Hello, this is Concrete Path. Today's lecture is about the problems related to bending stresses. So we have the problems. Take number one problem. Let's say this is cross section of the beam. So then after that, what you do one thing, you apply a load at the top, a tensile load at the top. So tensile force of P equals to 4 kilonewton. So this is our centroidal axis, or we can say principal axis. This is our principal axis. So if you had to get the maximum, you had to get the stresses at the top and stresses at the bottom of this beam. So you need to get the stresses at the top and at the bottom of the beam because of this loading. Since your load is not purely along the axial line, or we can say along the principal line, we can say you can transfer the force on the central line or the axial line or the longitudinal axis. So if this is a force 4 kilonewton, so if you want to transfer it on the onto the axial line, so there you have to say what is the free body diagram of this one. So let's say this is 4 kilonewton, then there would be 4 kilonewton here also, and balancing 4 into, let's take the dimensions of the beam as for 50 cross 15. So that means this part is 25 mm. So 4 kilonewton load is acting, and this will cause a moment of 4 into 0.25, so 4 kilonewton into 25 mm. This moment of that we can say this moment has been developed here, m. And similarly, this will be transferred onto that point. Let's say that this point is our reference. So we can say this is the force acting. This is the force acting. Or we can say this is the force that's tensile force, tensile, and a hogging moment. And a hogging moment is acting on this one. Hogging moment of 4 into 25 mm. So that value will be calculating. So let's take that value as m. So this force and moment would be transferred finally to the axial line of this member. So directly you can say that this force, the force 4 kilonewton, is trying to rotate in anti-clockwise about the center of that section. So finally this force has to be encountered, and then after that you can show other free body diagram also. But on the joint you can say that the force, because of this effect, you can have these two forces acting. So if you draw that, this is the cross section of the beam. This was your 50 cross 15, and that means a compressive, that means a tensile stress. Let's say this is tensile stress. That's uniform for the entire section. So we can say sigma tensile. That is direct because of that direct force, direct tensile stresses, and that equals to 4 kilonewton upon total area of that cross section, 50 cross 15 mm square. That's all tensile. All the fibers have tensile stresses. Now if you talk about that moment, so this looks like a cross section is here. We have this cross section, and about the centroidal axis, or we can say neutral axis, your moment is acting, or this is acting in this way, anti-clockwise moment. So we can have the fibers that the top fibers, because of this is a hogging moment. This is the moment should be in this anti-clockwise, because here it was clockwise and here it would be anti-clockwise moment. So that means on the beam, anti-clockwise moment is acting, that will make the fibers in this fashion. Let's say this was your beam and you are applying anti-clockwise moment. So this force, it got transferred to the along the axial line, so it would cause an anti-clockwise moment. So your beam would get hog curvature. Let's say this one. So top fibers will be having tensile stresses and bottom having compressive stresses. So this is our next stress diagram. So this is tensile positive and bottom compressive. So the stress value, we know stress value, stress equals to my by I, because because the section is symmetric, or we can say that y is same in both sides, y max. If you want to say sigma bottom, you need to write here y bottom, and if you write sigma top, you need to write my top by I neutral axis. So you can solve that. Once you got the moment was equals to 4 kilonewton into 25 mm, then the value of y was 50 upon 2 mm, and thereafter you have a moment of inertia about the neutral axis, so you can solve that BD cube by 12. BD cube by 12. That's BD cube by 12 mm power 4. Then after that you can have this one also, same value. So this is same value. This is same value. So finally you got the stress value equals to some value alpha. This is some value of beta, direct stress value of beta. So you got this value of beta. So you can say final stresses on the top. So you can say final stresses at the top of the cross section because of this general loading, because of the loading that was acting along the top line, because of that load P. So you have stresses at the top equals to, first one was your tensile and second one is also your tensile, so alpha plus beta. And similarly sigma at the bottom, sigma bottom would be equals to, at the bottom we have, because of the direct stresses we have positive stresses for positive beta, and because of that moment you have anti-clockwise, that so because of that you have compressive stresses at the bottom, compressive stresses minus alpha. So you got the stresses that finally we calculated that, and we got the values of 21.33 megapascal tensile, positive, we can say positive, and this one is your negative 10.67 megapascal compressive. Let's take one more problem. We have aluminum tube. Let's say this is the tube. Then its length of 2.5 meter. Then you're applying a force of 12 kilonewton. P equals to 12 kilonewton. Then you need to say what's the minimum required diameter. Outer diameter, d outer. Okay, so d outer. And if the thickness of the wall of this tube equals to d outer by 8, and sigma allowable in bending stresses, I can say in bending equals to 50 megapascal for this tube. So you have this one, that allowable stresses you can have in the tube that equals to 50 megapascal. So the thickness, we can say this is the thickness, that is d naught by 8, and let's say this is the diameter outer, so we can say d outer, and this is the inner diameter, d inner. So let's take the outer diameter as d naught and inner diameter as di. So we need to say if the allowable stresses is this one, that means the maximum stresses, that means sigma max anywhere, should be less than the allowable stresses, should be less than or equal to 50 megapascal. We don't want the stresses because of the loading to be more than the 50 megapascal. We have to design the thickness of the, we have to design the outer diameter in a way that sigma max anywhere along the section, in any section of the beam, any section of this of length 2.5. So this is the total length of 2.5 meter. So we need to show that we need to have that stresses lesser than the allowable stresses. So since the beam is prismatic, that cross section is same, remains constant throughout the length. So cross section remains same throughout the length. So we can say the maximum stresses would be at that means your y max and I neutral axes remain the same throughout the length. That means only the variable that is changing, that is a maximum moment. So we know that maximum moment would be at the end side, that if you apply a load of P equals to 12 kilonewton for a length of 2.5 meter, here the moment developed would be moment maximum would be equals to 30 kilonewton meter. 30 kilonewton meter. So we can say maximum stresses. That means we can say sigma max. That equals to the value of sigma max would be equals to m max y max by I neutral axis, and that should be less or equal to 50 megapascal. Now the value of moment that's maximum, we can show that equals to 30 kilonewton meter, or 30 kilonewton meter, and value of y max would be equals to, so the section that is resisting, that looks like a hollow tube. We can say this is a hollow tube, a tube. So this is the resisting section. So if you have neutral axis, so let's say this is the neutral axis, and total diameter or total outer diameter is d naught. And if you say what's the y max, y max would be equals to d naught by 2. So this is y naught or y max, that's d naught by 2, d outer by 2. So we can have those. And similarly, what's the moment of inertia, second moment of area about the neutral axis, that we have, let's assume that total it is a solid section, circular section, then we can say total moment of inertia would be equals to pi d outer power 4 by 64. Then you subtract the inner part that's hollow, so that area contributed would be equals to, you have to subtract that equals to pi d inner power 4 by 64. But we know that the inner value we can calculate if the thickness is, the value of thickness was given to you, thickness of wall was d naught by 8, thickness of wall was d naught by 8, d naught by 8. That means if you take any diameter, let's say this is the diameter, you would say what is this value. So total diameter, if you take total diameter minus twice thickness, that would provide you d inner. This is one thickness, and next the thickness, and this is the diameter, inner diameter. So inner diameter equals the outer diameter minus 2 times d naught by 8. So finally, you can have this 1 minus 1 by 4, 3 by 4, 0.75. So we can write 0.75 d outer. So finally, you substitute the values here. So we can write into your d naught by 2, then pi to the power 6, pi by 64, d to the power 4 minus 0.75 d to the power 4. That should be less or equal to 50 megapascal. And once you got this one, and you can have the outer diameter, that equals to 208 megapascal, 208 millimeter. Similarly, you can have internal diameter also, or you can say thickness of the wall also. So that is 0.75 of 208, that equals to 156 mm. That means the thickness of wall would be equals to 208 minus 156 by 2. Let's take one more problem. So this one is a beautiful problem of the bending stresses. Let's take this one. So you have steel beam. The cross section are, let's have the loading. That you have a simply support beam. And the loading is 5 kilonewton here and also 5 kilonewton here, and also a UDL of 1 kilonewton per meter throughout the length. 1 kilonewton per meter throughout the length, and the length, total length is 2 meter, 4 meter, and 2 meter. Now you have a cross section of the beam. Now the UDL is entirely vertical. UDL is perpendicular to vertical, parallel to vertical plane, we can say. Parallel to vertical plane. So, but the thing is that, let's say this is x-axis, this is y-axis, and this is z-axis. So this is the z-axis, this is z-axis, and this is y-y-axis. And this is let's say that the load, the concentrated load is acting in a way, it's making an angle of theta 30 degree. So the load is making an angle of theta equals to 30 degrees. So P equals to 5 kilonewton. That makes an angle of 30 degrees with the vertical axis 30 degrees. So we have, so these two loads 5 kilonewton and this one also, they are making an angle of 30 degree with respect to the vertical axis of the cross section. So cross section here, it looks like this one. So load is acting in this way. Here the angle at an angle of 30 degrees. So because of this one, if you resolve that force component along two directions, or we can say, let's say this was your vertical and you are applying a load of P in this way, and that is theta. That means the let's say this one and this one. Let's make the different color. So the component here would be equals to P sine theta, and in this way you would be having a component of P cos theta. So P cos theta, with that value of P was 5, and cos theta, that equals to this one, and P 5 into sine 30. 2.5 kilonewton. Similarly, you got this one, 2.5 root 3 kilonewton. So you have now two different loadings. One is along the vertical axis, and next one is along the horizontal, along the ZZ axis. So let's talk about the vertical loading first. Let's forget what was the component along that Z axis. Let's talk about only the vertical loading. That vertical loading of 2.5 root 3. So let's make the loading in such a way. You are only solving for the vertical loading. So let's say for the vertical loading, let's call it as vertical loading only. If this is vertical loading only, that means moments would be developed along the z-axis, moment z. So you are calculating for the moment z. So you had the loading 1 kilonewton per meter, for the entire length of 242, and the vertical load is acting, that equals to, if you solve the value, 5 cos theta, that 4.33 kilonewton. Now you can have the, so by the symmetry, can you say what is the maximum bending moment? Maximum bending moment? So clearly we can say in the form of some parabolic variation would be there, and maximum bending moment would be maximum at the mid. So if you solve for the reaction, the value of reaction comes out to be equals to 8.33. And if you solve the maximum bending moment, M max, or we can say that mz, that equals to 8.33 for the length of 2 2s are 4, 4, then minus 4.33 for the length of 2 meter, then minus a UDL of 1 kilonewton for the length of 4 square by 2. 4 square by 2. So you got the maximum bending moment equals to 16.667 kilonewton meter. So we got the loading in the Z, in the Y. If you want now stresses because of this one, stresses, we know stress equals to stress maximum stress equals to M max Y max by I neutral axis along the ZZ axis, along the ZZ axis, along the ZZ axis. So you have this section. The dimensions of the section are, this is 260 and this is 180 mm. So this is your ZZ axis or neutral axis for this case. Now what's happening that a load is acting, and you need to say, so the moment is acting in this way, moment Z. So because of that, you can say the stresses. Now the question was that you have 4 corners of the section. Let's call them as A, B, C, and D. We know that stresses will be maximum, bending stresses are maximum at the corners because the stress is proportional to y from the derivation, that maximum stresses would be at the extreme fibers as you go from the neutral axis towards the extreme fibers. Stresses will be maximum. That's why we are solving for the corners only, because if the corners are safe, that means internal part are also safe for the bending stresses. So you need to say what are the stresses at ABCD. Now, if say what should be the nature of the bending moment? What is the bending moment nature? So we know the nature of the bending moment would be positive, sagging bending moment. So curvature would be developed in this way, curvature. So that means top is in compression and bottom in tension. So tension and minus compression. So this is the configuration. That means the fibers, that the corners A, B, C, D. So we have the corners, that's AB is in tension and DC is in tension. And that means D and C are in compression and A and B are in tension. So if you write the bending stress formula now, if you calculate this value, you can write that maximum moment equals to that 16.67 kilonewton meter, 16.67 into 10 to the power 6 Newton mm. Then you have Y max. The Y max equals to value of Y max. This is along the Y axis, so Y max equals to 130. You can show 260 by 2 mm. Then you write what is the neutral axis, that second moment of area about the ZZ axis, that equals to BD cube by 12, B D cube by 12 mm power 4. Let's call it this value as alpha value. That let's say this is the value of alpha. So but we know that the stresses for the AB would be tensile and for the CD would be compressive. Now if you talk about the loading that was in the ZZ axis, so the component was along the ZZ axis, that was equals to P sine theta. So P sine theta. There's no any other load acting in that direction. So let's say the beam looks like in this way now. Let's say this was the beam. Let's say this is the beam. Now initially the loading was, this was your UDL 1 kilonewton per meter, and a vertical load was acting in this way. This was vertical load. This was vertical load of 4.33. Now there is also one horizontal load also. So one horizontal load. So this is one horizontal load, and this is one more horizontal load. Horizontal load of 2.5 kilonewton. So because of that, now that acts, let's say that acts along that center line, 2.5. So if you rotate if you want to rotate the beam 90 degrees anti-clockwise, if you want to rotate the beam anti-clockwise 90 degrees, so the loading would, and if say this was your B and this was your D, then after rotating the B would be upwards and D would be downwards. So if you make the beam in now in this way, that the dimensions were, let's make the dimensions also. Let's say this was your B was equals to 180 and the depth was equals to 260, and this was your ZZ axis, this was your ZZ axis, this is X axis, and this is your YY axis. So for this one we have YY axis as critical, YY axis. So neutral axis is YY axis, neutral axis. So load is acting at this point and at this point, 2.5 kilonewton. So line diagram can be shown in this way, 2.5 and 2.5, and the reactions would be also equals to 2.5. Let's say this beam, and we can say maximum, because of the symmetry of the loading, we can say maximum bending moment would be at somewhere at the midspan. Let's say there is some linear variation. There might be some kink also, but let's forget about that kink. Let's say that the bending moment maximum would be at the mid, M max, but that is in the y direction. That's in the y direction because load is acting in z direction, and the resistance would be, load is acting in the z plane, so moment would be developed in the y plane. If you take that line as y line, this is y line, and moment is acting in the the direction of moment is in the y direction, but it is acting for the plane zz. So your my would be developed, that my equals to maximum moment. So this was your 2 meter, this was your 4 meter, this was 4 meter. That means maximum moment would be equals to 2.5 kilonewton into 2 meter into 2 plus 2 meter. Then after that minus 2.5 into 2 meter. So finally you got a value of 5 kilonewton meter. And if we talk about the that y max, here the y max won't be there. We have that z max. So this is the neutral axis, y, or we can say neutral axis. So there would be z max because this is along the z axis. So z max would be equals to 90 mm, and I neutral axis would be equals to I y, that equals to BDQ by 12. So finally you substitute the values. So you substitute the values that we can say sigma in x because of loading in z. So that is equals to 5 into 10 to the power 6 Newton mm. So this is your m, and y max would be equals to z max 90 mm. Then after that Iyy equals to 260 into 180 cube by 12 mm power 4, and you got a value of alpha, and you got this value as beta. Let's say this is the value of beta. But if you talk about the cross section, initially the cross section was ABCD. So let's have the ABCD. So this was A, this was B, this was C, and this was D. ABCD, yeah. This was ABCD. Now if you rotate it 90 degree rotation, now you rotated the cross section by, or beam by 90 degrees. So this B would get lifted up. So B got lifted up. So let's say the B got lifted up. Initially the B was here, so it got lifted up by that 90 degrees. So B, then after that, then you could say this one is your A, and similarly this one would be your D, and this one would be your C. ABCD. Do you understand this? So this would be your DABC. Now, because now the moment is acting, that is a sagging bending moment. If you talk about the bending profile, that would be some sagging curvature. So top would be having that compressive stresses, bottom tensile stresses, because bending moment is positive, sagging bending moment. So we got the profile that. Then finally we can say out of those four, compression is having for the corner C and D, C and B. C and B is having C and B is having compression, and A and D is having tensile stress, AD. So we can say stresses in x direction at the point A, at the corner A, that would be equals to, initially the value was alpha, and beta. Similarly, let's make the values first. Stresses in x at the corner B, stresses in x at the corner C, stresses in x at the corner D. That is alpha, beta, alpha, beta, alpha, beta. So these are the values. Now we have to say what's the sign for those all. So let's talk about the corner A for the vertical loading. For the vertical loading, we had value of alpha, but at the corner A, it's saying that you have tensile stresses, and for the B also you have tensile stresses. Both have tensile stresses. A and B is having tensile stresses of alpha. That means we can write alpha plus and plus alpha. That means these two have minus alpha because they have compressive stresses. Then after that, if you talk about for the vertical loading, this was for the vertical, we can say py, and this was for the that pz for the load in z direction. Then for the load in z direction, you have beta value equals to, for the A and D you have tensile stresses. For the A and D you have tensile stresses. So let's say this was your A, it's having positive tensile stress, and for the D you also have positive tensile stresses. And for the CB you have compressive stresses, that means negative and negative. So finally you got the values. Finally you can calculate the values alpha beta. So the values of, let's write the values also. Let's say Iyy comes out to be equals to 126.36 10 to the power 6 mm power 4, and similarly Izz, let's say Izz value comes out to be equals to this value, Izz equals to, that value comes out to be equals to, yeah, Iyy was equals to 126.36. Similarly, Izz, if you calculate Izz, that would be equals to, let's write here, this was your Izz, equals to 263.64 10 to the power 4. So finally you got the values of stresses. Let's try the value of stresses. That means stress at A equals to tensile stress of 11.78 megapascal tensile, and for the B you have 4.652 megapascal tensile positive, and for the C you have negative 11.78 compressive, and for the D you also have compressive minus 4.652 compressive. So you can see that one of them have positive behavior and next one is having negative positive. That means tensile stress, compressive and tensile. So there were 4 points, 4 corners, A, B, C, D. So A and D is having opposite sign because of this diagram. Net diagram would be somewhere, some sort of diagram would be there, net. So because of that, you have tensile stresses net at the bottom and compressive stresses net at the top. And similarly for the C and D, you have some stresses of some stress values of 4.652 positive here, tensile, and here some compressive. So now the question says that get the location of neutral axis. That resultant neutral axis, we can say, because loading was at making an angle of theta. So we said that this is your y axis and this is your z axis. Then we calculated for two neutral axes. We said for the first case, for the vertical loading py, you have neutral axis of ZZ. And similarly, you have for the horizontal loading, you have neutral axis of YY, neutral axis. So there would be net resultant neutral axis somewhere in this way, that if this was your one neutral axis and this is your next neutral axis, and load is resultant load would be somewhere in this way, that load the load is acting in this, making an angle of theta. That means perpendicular to that loading plane of bending, that would be net resultant, because perpendicular to the plane of bending, the neutral axis would be there. So there's a chance that neutral axis would be somewhere in this way, through the centroid, passing through the centroid and making an angle of making some angle, that we have to say where is the location of that neutral axis. That's our job, to find neutral axis. That's resultant neutral axis. So you can say from the definition of neutral axis, we say that it is the locus of those points, where the bending stress is zero, where the net bending stress is zero. Because we can say net bending stress is zero. So if you say we have two stresses, one is your sigma x because of loading y, and sigma x because of loading z. So if you add them, and you should equate them to equals to stress value of zero. If you have the equation m max y by I, let's call it as mz, then we write izz, then plus m y z by I yy. That should be equals to 0. But if we talk about that, let's take any particular corner. Let's take any particular quadrant, we can say. Let's take the quadrant, this one. If you take this one, if you take this quadrant, that's having D, and this is origin, center. So if we say that let's talk about this section. Let's talk about that section. So we say if you go from neutral axis, that was your ZZ neutral axis. If you go from this one to some y value, and if you go from this neutral axis that was along the YY neutral axis, if you go from this one to some value of Z, you don't go to Y max or Z max. You don't have to go Y max or Z max, because there is a bending stress there. We have already calculated that was equals to bending stresses at A, B, C, D. That won't be equals to 0. That's not 0. So we have to go to some value of y and z such that the bending stress is equals to 0. So you write that we have to go to some value. We need to go to some value of that z and y, such that net stress would be equals to 0. That we can call as neutral axis. So there's a chance that the neutral axis would be along this one would be neutral axis. There is a chance, high chance, because the load is acting in this way. Perpendicular to that, there is a chance that somewhere it would be their neutral axis. In this corner, there is less possibility. Had the load been in this direction, you could have said that there is a chance in this direction somewhere you can get. So if you take this element, if you take this one, this section that's having corner D, so let's talk about that. So you go to a distance of y and z. There is some point where the stress is 0. So let's say where is that point? If you take that from the origin, what's the angle it's making? If you got the angle that would be a straight line, then we can join the straight line. So we don't know that alpha. So finally that we can write the equation now. mzy by izz plus myz by iyy. But for the corner D, you have to see that the value of alpha and beta was in terms of negative or positive. You have to see that also. So for the corner D, so that means in the region that's having D and the origin. So this was the ABCD. We have this ABCD. This was ABCD. So for this region, we are talking about this region. In this region, you have alpha as negative and beta as positive. Alpha is negative and beta is positive. So you have to keep the sign also. So alpha is negative and beta is positive. So if you substitute the values of mz, the value of mz was equals to 16.67 kilonewton meter, and value of y would be some value, and izz was equals to 263.64 into 10 to the power 6 mm power 4, and that was in my negative sign, plus you add that my, the value of my was equals to 5 kilonewton meter, and there is some value of z from the neutral axis, so we say and divide by iyy, value of iyy would be equals to 126.3610 to the power 6 mm power 4. That should be equals to 0 because we want stress to be 0. So finally you got some equation of minus 0.0632 y plus 0.0396 z equals to 0. So if you have that, if you say we had this one corner D and this is center O, or says that centroid, so let's say the point is somewhere here. So if we know that the equation is a linear function of x and y, so there is a linear variation. So let's say this is the alpha, and this was your value of, we go to the some value of along this neutral axis, along this yy, we go to some value of z, and along that zz axis we go to some value of y. So this is z and y. We can say tan theta, tan alpha equals to y by z. So y by z. If you substitute here y by z, so we can have this value of y by z equals to some value of this one, that 0.0396, then divided by this 0.0632. So finally you can say alpha value equals to, the value of alpha equals to 32.07 degrees with respect to that horizontal, with respect to zz axis. So you got the value of 32.07. That means the neutral axis would be formed at an angle of 32.07. So final neutral axis would be at an angle of 32. So this is angle of 32. So we have this neutral axis. So this is the neutral axis, net neutral axis, 32.07 degrees. So perpendicular to that, you can say perpendicular to that there is a plane of bending. So this was a very beautiful problem of the bending stresses. Let's take one more. Let's take next problem that we have. We can call it as a next topic. We can take the next topic. We can take the next topic. That's called as fully stressed beam. Fully stressed beam, or we can say beam of constant strength. So actually we design in a way that, let's say general design, it looks like this, that we calculate the maximum bending stress, maximum bending moment, that equals to PL, and then you say the maximum bending stress equals to that maximum bending moment into y max by I. The value of I was equals to same. The value of I was same because we kept the same constant cross section. We kept the same cross section throughout the length. Then we say y is also same, I is also same, but the bending stress maximum would be equals to P into L. So we said that let's design for the that section that's close to the support, that fixed support, where the maximum bending moment is there. If you design that section, rest of the sections would be safer because the stresses would be lesser. If you design for the prismatic beam, if you say what are the stresses at this location, you design it for this section only. You design for this section that the stresses here would be lesser than the stresses, we can say design strength of this one. It is having some design strength that is more than the stresses that can be developed because of loads. So once you said let's have this section designed, then after that you keep a constant cross section throughout the length. So based on this one, we said that it's not a proper utilization of material. We said that it's not a proper utilization of material. It's not a proper utilization of material. Now we want to say we want to maximize the savings, material saving. We want to say the material maximum. So for that, you should say we should make a beam such that every section of the beam is having stresses. That means stress should be less than or equal to that allowable stresses on that particular section. So that allowable stress is a function of material. Allowable stress is a function of material. And the cross section. Let's say that it's a function of material. So we have to keep the material in a way that we have to change the dimensions of the section such that the stresses developed at that point that should be equals to or less than or equal to sigma allowable. So this is the goal, that you have to vary the cross section. That means you have to vary the moment of inertia. You have to vary the moment of inertia of the cross section at each section. Because the bending moment is a linear function. So if you also make the depth as a linear function or width as a linear function, it depends on the loading and the function which you are keeping constant. So we have two variables in the moment of inertia. One is your width and next one is your depth. So we have two variables. If you keep one fixed and next variable, you can have the relation of those the relation we can derive that thereby. So that means the beam, we want to say that stress maximum should be there. We can say that there should be maximum stress on every section. We don't want we got this that end section we got safe here, but we don't want this part to be less utilized. We want it to be fully utilized. We want to say, let's have the stresses we are having here. Let's say stress 1, we want stress 1 here also. We want stress 1 also here, and here also. So for that, you have to change the dimensions such that the stresses would be same everywhere. So let's talk about the first case. That you have this cantilever loading, that loading of P for a cantilever beam. Now you want to say, I want that fully stressed beam or maximum stress should be at every section or at every cross section. So for that, how can you go for this one? Let's say this is let's say there is some section. We don't know what is the section, how is the variation of section. So let's make it as a line first. We don't know the section. So but we want sigma max everywhere. So we want sigma max. What is the equation for bending stress? We know that bending stress equals to moment max y max by I neutral axis, and we want it to be sigma. Sigma should be constant. We want sigma to be constant. That means sigma is constant. If you want sigma to be constant, then we can say at every section we want stresses to be same. That is stress sigma. So that we can say m at any x, y at any x, and I at any x. We can have this one in this way. So we have two variables in the moment of inertia, I neutral axis. That's b d cube by 12. Let's say this is b d cube by 12. So we have b and d. Let's take the first case that let's keep the b. Let's fix the b. Let's say b is fixed. That means you have to vary the depth along the length of the member. So this is the length. Let's talk about some value of x, where we are worried about that how much depth we should have that at that particular location of x. So if you write the equation for that, so we can say that your maximum bending moment would be equals to P into L, and y max would be equals to, let's say the y max at the end would be some depth d and some width d. Let's say the maximum depth we are providing at equals to d, and the y max would be equals to d by 2, and neutral axis would be equals to bd cube by 12. I neutral axis bd cube by 12. So this is the part we know that at the end we know that we have given stresses, that we have sigma max there, we have y max there, that we have stresses known to us, we have m max known to us. So we should know the value of b and d at the end, but we are varying the dimensions along the x. So for that particular value of x, we need to get the value of dx. So let's write the moment at any x that would be equals to p into x. Moment at any x equals to p into x. Then after that, the y max would be at any x equals to dx by 2. Similarly, you have width kept fixed. If the width is kept fixed, that means b is constant throughout the length. That means you have some dx cubed by 12. So finally, you have some value of dx square, dx equals to, or we can say dx square equals to x by L into d square. So if you say that that depth at any x is a function of root x, is a function of root x, is a function of root x. So if you equate it to the stress, that stress is constant everywhere. So at each section, at each cross section of the beam, we want stresses to be constant. If you equate now stresses with the variable dx, so we got equation of that dx equals to dx square equals to 6 times p into x divided by b into sigma. So we got this equation. So we got this equation in terms of sigma. And we have the parameters that are fixed. One is your b is fixed, sigma is fixed, and the load is also fixed, but only the variable that is x. So we would say dx is a function of root x. So next one is that if you now kept the depth constant, depth is fixed. So if you want to vary the width now, so we can say sigma equals to m max y max by b d cubed by 12 equals to moment at any x, px, and depth we have kept constant. Depth is constant, d by 2, and width is varying now, bx, so d cubed by 12. So we got equation of bx equals to x by L into b. So bx is a function of x power 1. So similarly, if you want to equate it with the stresses, so we can write bx equals to 6 times b into x by d square sigma. So this is the equation we got. 6px by d square sigma. So similarly, if you want to say what should be the value of width at at the x equals to 0. Let's say this is the beam. At x equals to 0, b at x equals to 0, that equals to 0, and b at x equals to L, that equals to 6pl by d square sigma, and b at any L by 2, that equals to 3pl by d square sigma. That means it's a linear function. So the width from the top, you can show that from the top you have a width of varying width. So we got a final maximum width of b max equals to 6pl by d square sigma. So we have width of 0 here, and we have width of 3pl by d square sigma at the mid. So this is the variation of the width. This is from the top view. If you have from the top view, this is the top view of the beam. Similarly, you could have solved for the depth also. So if you solve it for the depth also, so you can say depth at the end equals to 0, and depth at the support side, that is d at L, equals to 6pl by b sigma. And similarly, you can have for the midspan also 3pl by b sigma, and there is a root function of that variation. Then after that, if you have simply support beam, if you talk about simply support beam now, let's talk about simply support beam, and load is at the midspan, and let's say total length is L, so we can keep the variable of x such that x is between 0 to L by 2. So we can say reaction would be p by 2, and we want to vary dx or we want to vary bx. such that sigma is constant everywhere. Such that sigma is constant everywhere. Let's talk about that. Keep d fixed. If you keep the d fixed, depth is fixed, that means you are varying bx. So we can say sigma equals to what's the maximum bending moment we can have? What's the maximum bending moment we can have? PL by 4, PL by 4, PL by 4, and maximum depth we can have d by 2, and maximum we can have bdq by 12. That equals to what's the moment at any x? So we got a moment of p by 2 into some value of x. So p by 2 of x, p by 2 of x, p by 2 of x, and there is some depth. D is kept fixed, that means d by 2, and b is varying bx dq by 12. So we got a bx function of bx equals to x by l into b, x by l into b. And there is one more thing. That's 2 to the 4 to the 8. There should be some value of 2 also. So 2x, I think. 2x b by l. I think 2x by l, I think. If you solve this, this part, d by 2 is gone, d by 2 is gone. This is also gone. So we are left with b into x by l, and thereafter we are left with this 2 1s are 2 2s are 4. So we are left with that 2 times. So we got this value of that. We got this value 2 times. I think this is correct. So we got this value of bx equals to x by l into b. And after that, so this is a linear variation of x. So if you want to equate it with the stresses, so we can say b at any x equals to we can say that equals to p by 2 into x into d by 2 divided by d cubed by 12 into sigma. So we got this value. So you can solve it further. So we got the width at any x. Similarly, if you want to say I want to keep b fixed, keep the b fixed. If you want, I keep the b fixed. So I say sigma equals to that maximum bending moment was PL by 4, and now the depth maximum would be equals to d by 2, and bd cubed by 12 would be I neutral axis maximum. Then after that, you have to vary the width, you have to vary the depth, so we write moment at any x px. Yeah, actually it should be p by 2 of x. Yeah, we got this one. P by 2 of x. Yeah, p by 2 of x. P by 2 of x. P by 2 of x. Then after that, you're varying the depth. So that is d at any x. We can say d at any x by 2. Then after that, b is fixed. Then dx cubed by 12. So we got some value of dx square equals to d square into x by l. And there is one more, that 2 times also. So we said dx is a root function of x. That root times x. This is proportional to root x. Then if you want to equate it with the stresses, so we can say dx square equals to that 3 times 3px by b sigma. So finally you can write in this way, 3px by b sigma, 3px by b sigma, 3px by b sigma. Yeah. So similarly, if you wanted to say what's the value of width at, so let's forget that. Let's take the third case, that's UDL. That's UDL. So UDL, and we know that loading intensity of W, and the reaction would be WL by 2. We know that maximum bending moment would be at the midspan, WL square by 8, and moment at any x equals to WL by 2 into x minus WX square by 2. So the thing is that if you equate that moment of resistance with the maximum bending moment, yeah, or we can say moment at any x, or moment at maximum moment. Yeah, if you equate the moment of resistance with the maximum bending moment, we know that moment of resistance is sigma. We want sigma max to be equals to sigma. That means we want sigma to be constant everywhere. Sigma is everywhere, every section. let's say there is some sigma into some value of bd squared by 6, that equals to some moment of wl by 2, then we have x minus x square. Is it okay? Yeah, it is in terms of this one, w by 2 lx minus x square. Then if you want to say what's I should keep the b as fixed. If you keep b as variable, then we want to say for bx to be maximum, we want to say we can say minimum, then we then differentiate it with x, and you get a value of bx equals to 3wx square by bx dx square. You can also solve it by in this fashion, that if you want to keep b fixed, first case, that if you want to keep b fixed, you say that sigma equals to wl square by 8, maximum bending moment, and d is fixed. Yeah, d is variable, that means d by 2, and b dq by 12. This is the first case that we have to equate with moment at any x, wl by 2 x minus wx square by 2. So this part we have. Then after that we have depth at any x divided by 2. Then we have width constant, then depth x cubed by 12, dx cubed by 12. So then the equation becomes very long. So you can calculate that also, that what's the value of d at any x. So you can have that equation. That in terms of some value wl by 2, yeah, w gets cancelled, so we are left with that lx minus x square by 4 by 8 by 4 by 8. Then we have also that d square and divided by l square. Then we multiply that 16 also. So there is some equation we got. So that we can say that's a dx is a function of root x, or we can say that's a function of x. It's a function of that lx minus x squared. That means it's a function of this one. So if you want to say what's the variation of if you keep the depth fixed, that means you are varying width. B is getting varied, so we can write sigma equals to wl square by 8 into maximum moment, so we into d by 2 bdq by 12. Then that should be equals to moment at any x, wl by 2 into x minus wx square by 2. So this was your moment, and depth would be constant, d by 2 into width at any x, dq by 12. Similarly, you can write that. So we can say width at any x equals to b times x. Actually, it would be in terms of lx minus x square, divided by 4, divided by 2, then we are left with that 8 also here on the top, and divided by l square. So this is the function we got. That bx is a function, that bx is varying in this way. So if you want to say I want that width to be minimum, if you say I want width to be minimum, so for minimum width, or means saving, I want saving to be maximum, that means bx should be minimum. So if you say dbx with respect to x, if we differentiate that function of width, so we can solve that equals to 0, then we can say that means we got a value of l minus 2x equals to 0. So we got a value of that x equals to l by 2. So that means that width would be maximum at l by 2. If you say what's the value of width at 0, so this was your beam of simply support. So we take x from 0 to l by 2. So if you say what's the value of 0 and that width at 0, so we get a value of width equals to 0 from this equation. We got a value of 0 at, so similarly, if you substitute value of b at any length l, if you want to say what's the value of width at any l, because this is symmetric, we can say length is also, width should be 0 at the end also. So If you substitute here L into L square minus L square, that is also 0. So we got a width of 0 and 0 at the ends. So this is the beam from the top. So we got a width of 0 here, and we got a width of 0 here. And we want to say we have solved that maximum width would be at, maximum width is at L by 2. Maximum width is at L by 2. If you substitute value of x equals to L by 2, so we can say B at L by 2 equals to B times L into L by 2 minus L square, 8 by L square divided by 2. So you got a value of that we can say B by 4 L square 8 by L square. So you got a value of B, twice B. But what's B? You got a value of 2B. So but the B we don't know what value of B. B at L by 2 equals to B. What is the value of B first? If you solve it in terms of stresses, let's solve it in terms of stresses. Let's solve it in this way, that we have stresses equals to WL by 2 minus WL by 2 into x minus WX squared by 2, and you have depth by 2, and after that you have bx into d cube by 12. So we want that bx to be maximized. So let's say bx equals to WL by 2 let's keep in this way, W by 2 Lx minus x square into that divided by d square into 6 here top. We can write 6, and we have sigma. So if you want to say we want that maximum width, to be maximum, so we can also get here also that dbx by dx equals to 0, then we can get x equals to L by 2. Now you got that. If you say what's the value of width at 0, that's also 0. Width at L, that's also 0. So finally you got 0 and 0. Then you want to say what's the value of B at L by 2. So you substitute the values, that we can get 3W, then L square by 2 L by 2 minus L square by 4. Yeah. L square by 2 minus L square by 4 divided by d square sigma. So you get a value of, width value of equals to some value of width. So some value of width, that B at L by 2 equals to 3 times that you solve that 3 by 4 times WL square by d square sigma. So, and the function is a parabolic function, we can say quadratic function. So there is a width variation in this way from the top. So this is your width variation of this beam, width variation. So Bmax at mid. Let's have the next topic that's called as anticlastic curvature. Anticlastic curvature. So you applied a sagging bending moment on the beam in the long direction, longitudinal. So we can say this is, you applied moment in the z direction. So what's happening on the beam? It got sagging curvature. It got sagging curvature. So sagging curvature got developed. Because of that, there was compressive strains developed on the top fibers and tensile strains on the bottom fibers. Now we know Poisson ratio. Do you know Poisson ratio? Poisson's ratio mu. It says that because of the longitudinal strains, these were your longitudinal strains, long strains, E long. Because your longitudinal strains, the lateral strains would get developed. So if you talk about the lateral strain, if you talk about this now, so let's say this was your beam before. Now you applied moment in the z direction. This was the z direction. You applied moment, but because beam has got compressed on the top fibers, that means that on the other side of the beam, on the lateral side of the beam should get elongated. And similarly on the bottom fibers, your beam got stretched. That means on the bottom fibers, the bottom fibers should get compressed. They should get compressed. Then finally you can show this was your before bending. This was your lateral side or section side before bending. Then after that, it would become in this fashion. It would become in this fashion now. So this was your B, this was your D. Now it has become D, and this was your B1, and this is your B2. So the width has been changed. This is what we call as effect of Poisson ratio. Now we had the neutral axis here. Here the neutral axis we had. We said that let's form a circle. Of radius of curvature equals to R. From the neutral axis to the center, we had radius R, that we had radius of curvature. Similarly, here we have the beam has bent in the cross section also. There would be some neutral axis also. So if you draw the circle of that, if you make the circle of that, let's make the circle of that. So we can say this value of radius, you can say this is neutral axis, and this value of radius that we call as R dash, that is called as anticlostic curvature. Now, if you say that what is the value of Poisson, what is the value of strain? We know that the derivation, we had the strain along x direction. We had this x direction. We said that strain in x direction equals to that y by r, the depth, that distance from the neutral axis, y by r. And if you talk about what's the strain in z, strain in z equals to, we know that equals to minus mu times strain in y, strain in x, isn't it? That strain in z equals to minus times mu strain in x. That is lateral strain equals to mu times longitudinal strain minus times mu y by r. So we got the value of Ez. Now similarly, if you want to derive the equation for that variation of strain along the cross section, along this section, you can say that strain in z, this is your zz axis, you can say strain in z. So we can have here that they are getting that stretched and bottom fibers got compressed. So you can say strain in z equals to some value of y. Let's say this is value of y by r dash. We can say that we have different radius of curvature that we called as anticlostic curvature r dash. Now if you equate those two, firstly you have minus mu. If you take the mod of that, minus mu y by r is that equals to minus mu y by r, then that equate to y by r dash. Then we can say that your r dash equals to r by mu. So that we have anticlostic curvature is the actual radius of curvature along the long axis and divided by mu. So this is your anticlostic curvature. So we have that now beam of composite section. Beam of composite section. So we have the one property of composite section, that we have the concept of strain compatibility. That means strain in one at the junction would be strain in two at the junction. At the same junction, this one, strain would be same for the two. So beam of composite section. Now we have two cases here. Let's talk about the first case, that we have connected the two members, but they are such that they are rigidly connected. Either we have glued them, let's say we have glued them, or we can have that bonded together. Let's say we have bonded together. So the meaning of that rigidly connected members or composite section, that means they will bend together. they bend together. If they bend together, that means only one neutral axis is there. Neutral axis is only one, and similarly you have radius of curvature only one, some radius of curvature with radius equals to r. So we have only one radius of curvature and we have one neutral axis. That's the definition of that rigidly connected. So we have symmetrically, in that we have first case that is called as symmetrically connected, that composite section. If you say I want to use a material, let's say this was your wood material, and after that I use steel sections on the top. So this is the steel sections I am using on the top and bottom. Let's say this is steel. So this is your steel on the top and bottom, such that I have equally placed the steel on the top and bottom. So I can say this is some thickness of T, and this is also thickness of T, and width of wood and depth of wood is equals to D, and let's say B is also constant. So I can say from the symmetry, I can say neutral axis would be somewhere here. That's at the centroidal axis. So I can say neutral axis is equals to centroidal axis. So in this case of that symmetrically placed or symmetric composite section, I would say neutral axis is easy to find because it is at the centroid. It's easy to find. You can directly say it's at the mid. Similarly, you can have that same that if you had that two different wood sections and you place a steel section in between at the mid. Let's say this is some steel section. This was wood, and this is steel, such that we can say neutral axis is at the mid. Now, if you say what's the strain variation, if you take this one and say what's the strain variation, we know that if the section is composite and if the section is composite such that it is rigidly connected. If it is rigidly connected, that means you have only one neutral axis, or you have one radius of curvature. You only have one radius of curvature. So if the bond is rigidly connected, if the bond is here rigidly connected, that means you only have one neutral axis, that is this one. So we have strain is 0 here or stress is 0 here. So we can have linear variation then. We say that there is a linear variation of strain. So this is your variation of strain. So we can say at this section we can have that strain in wood equals to strain in steel, that equals to E1, and we have here strain in S, that is Emax, let's call it as Emax, and we have also here strain in steel, that is Emax. But the strain here is some value, but both are having same value of strain. So we can say strain in wood, maximum strain in wood is equals to strain 1, and that is ES. Here we have represented that ES. So maximum strain in wood, that is the strain in strain 1, that is strain in S. But the maximum strain in steel is Emax, that's at the top fiber. So we got the linear variation of strain. Then after that, if you say what's the variation of stress, so if the strain is fixed, let's say if the strain at the junction is same, strain is same at the junction, but stresses won't be same at the junction because we have Hooke's law, strain into E. So stress is a function of E also. So if you have more modulus of elasticity, constant Young's modulus, if you have more Young's modulus, that means you have more stresses. So if you plot the stress variation, let's say this was the neutral axis. So you would say this was the reference line. I would say let the stresses in the steel would be some value of stress max, sigma stress in steel max, and similarly you have stresses in steel, that's max. Then after that, you know that stresses at the junction, at the neutral axis is 0. Then there is a linear variation. Let's say up to the junction there is some decrease of stress. Let's say the stress decreases to this value, sigma S1. But after that, since the strain is same at this junction, we can say for the steel you have stress sigma S1, but for the wood, if you go just to the wood section, you can have sigma wood, that equals to strain 1 into E wood. And similarly, you can have sigma S1 equals to strain 1 into E steel. So we know that E steel is greater than E wood. If you know that, that means stresses in steel is more at this junction as compared to wood. So that means the stresses in the wood would be lesser than that. Let's say the stresses in the wood is this part only. Let's say this is the stresses in the wood. Stresses in the wood. Stresses in the wood. And you have to go down by this amount. Then after that you have a linear variation after the 0. Similarly, you have this variation of stress in the wood. So say this is the stresses in the wood. Stresses in the wood. Then after that you have to suddenly drop by this amount. So you have to drop by this amount. So you have to drop by this amount. So this is the drop. So this is the drop. We can say this is equals to sigma S minus sigma W. So we got this value, this total value of this was your sigma S1, this point. This is sigma S1, and out of this one, this is your sigma W. And similarly, you have sigma W. Then after that, a rise such that overall value of that sigma S1. After that, you have to decrease that value downwards. So this is the variation of stresses. So this is the stress variation. So if you want to make it now in a more detailed way, let's make it in this way, that initially the stress was sigma S max, then after that it decreases by some amount. After that, the value here, this value would become equals to sigma S1. Then after that, you have the stresses in this wood that equals to some sigma W. Then it becomes 0. Then it becomes 0 here. So this is sigma W. Then after that, you have some sudden increase. Then after that, you have sigma S max. Sigma S max. This point, this is sigma S1. This point is sigma W. So similarly, you can join the 2 points here now. So this is the strain variation, stress variation. Strain variation looks like only this part, 0 strain, same strain. So you can also write that stress W equals to strain 1. Even the strain is same, but the EW is different. So sigma S1 equals to E1 strain, that's ES. Now, if you want to solve it, we have one method. If you want to solve these composite sections, we have this method of that we call as transformed section approach. So what we do that we transform one of the materials into the other one. So by replacing we know that strain is same for the two materials at the junction. We replace the material. We replace one material. Such that the effect of its E. Let's say we replace steel. Let's say we replace steel by W, wood. If you replace steel by wood, so that means the effect of strain is the same. We don't have the strain effect here, but the effect of that stresses because of that change in E. Because of the change in E, we say we have some modification factor, or we can say that's also called as modular ratio. Let's say that ES by EW. We have this factor also, and it helps us to convert the one material into other. That we also call as modular ratio. M, or we also called it as a modification factor. So we'll solve on a problem on it, and you would understand what is this, what's it doing that. So we transform one of the material into other. Then the section gets changed into some section. Let's say this becomes the final section, transform section. Then we calculate the neutral axis location. Next step is that we calculate the neutral axis location. Then we calculate the moment of inertia about that neutral axis. Then after that, we calculate the stresses at the top, at the junction, stresses at the top, at the bottom, and at the junctions. Then after that, we say what is the actual stresses? What are the actual stresses in the beam at the top, at the bottom, at the junction? Then we say what's the actual stresses. These were your stress in the transformer section. Then we say what are the stresses in the actual section. Then we have the modification factor here also. So these are the steps we do in the transformer section approach. So if you take that, if you take the problem, let's say we are taking the problem. Let's say we take the problem 1 on this concept. Let's take the problem number 1 on this concept. So we have a problem that's called as, that's saying that we have rigidly connected members, rigidly connected unsymmetric section. And unsymmetric means that you have two different materials, but they are connected rigidly. That means they have same neutral axis. Neutral axis is only one, or radius of curvature is only one, but the materials are different. That means one is of brass, next one is of steel. So the depth is 10 mm. Similarly, you have also 10 mm, and the width of the section is 40 mm. Now, the unsymmetric means you have different materials, brass and steel, and we have stresses, that sigma allowable also, that sigma allowable in bronze, sigma B allowable, that should be equals to 75 megapascal, and stresses that are allowable in steel, that equals to 112 megapascal, 112.5, and E of the bronze equals to that is 0.82, 10 to the power 5 megapascal, and E of the steel equals to 2.05, 10 to the power 5 megapascal. So question says that what should be if we have some simply support beam of this section, that's unsymmetric section, rigidly connected. You have this section for the length of 1 meter. You have this section for the length of 1 meter. What should be the load that I should apply at the midspan? P max that I should apply at the midspan. Size that. So total length is 1 meter. What should be the maximum load that should I apply at the midspan? Size that you have the stresses allowable. You have the stresses allowable here, 75 and 112.5. So from this beam, we can calculate the maximum bending moment. Can you calculate that? That equals to P max L by 4. So we can say that is, let's say the P is in Newton. Let's say the P load is in Newton. So we can write P. The value of L was 1 meter. So we can write 1 meter, or we can say 1000. Then we can write Newton mm by 4. So that's 250 P Newton mm. So that's maximum moment. Now we're going to say, since your section is unsymmetric or it's a composite section, so you can't directly calculate. Had it been homogeneous section, you could have solved that this was your maximum stresses, my by I, my max by I neutral axis. This was easy. But the thing is that you have a composite section. We have already seen that the stress variation was somewhat in this fashion. Some stresses. So you can't directly calculate that in this fashion, because this and this is not same. So you have this stress variation. You have some sort of stress variation in this way, and this is not similar to this. This is not same. So you have to say, let's convert one of the material into other. Let's convert steel into brass. So we can apply the method that's called as transformer section approach. So first step is that let's convert. It's up to you what you can think of. Let's convert steel into brass. That means you have to make some modification factor also, that we are also called as modular ratio. So the one you are converting, you should write its ES at the top. So you have to write ES by E bronze. That's modification factor. So the value of modification factor equals to 2.05 into 10 to the power 5 divided by the value of EB was equals to 0.82, 10 to the power 5. So you got some value that equals to 2.5. So you have some factor of 2.5. And one thing is that you don't have to increase, you don't have to change the dimensions in terms of depth. You have to keep the depth fixed. In this transformative approach, one statement you have to write, you only vary the width. You change the width change by that modification factor, but the depth remains constant. Depth remains constant. We don't have to change the depth, as the stress is a function of linear variation of y. So we say that we don't vary the depth. You keep the depth fixed. Only you vary y. That m, that would only vary the m, only vary the width. So if your width of steel was initially 40 mm, initially the width was 40 mm, and you are converting steel into brass. If your brass was initially there, that means brass part would remain as it is. Brass part would remain as it is. So brass part would remain as it is. So it would remain as it is 40 mm. This was your brass, and the depth would remain also as it's 10 and 10. So depth would remain same, 10 and 10. Next one is also 10. But you have to change the width of that. So we have to say, we know that because the steel is having stresses more, it can take more stresses because it has having more value of E. So that means it's if you want to replace that material, if you want to replace steel by brass, you have to multiply that factor 2.5 into that width, because effect of steel is more as compared to brass. It's resisting more stresses. That steel is resisting more stresses. So if you want to replace that steel, you have to multiply that width by factor of that 2.5. So that we can say 40 into 2.5. That 100 mm. So that means if your brass was there and steel was there, that means 40 mm of steel would do same amount of work as the 100 mm of steel, as the 100 mm of brass. As the 100 mm of brass would do same work, 100 mm of brass equals to 40 mm of steel. That is the meaning of this transformer section. So you have to make the width such that the width equals to 100 mm and the width remains same, 10 mm. This is 100 mm and it is also brass now. Entire section is of brass now, and I would say this is your depth of 10. And now the second step was to calculate the neutral axis. Now second step is that location of neutral axis. Location of neutral axis. Let's say from this from the bottom side, we can say this is some at some y value we can have neutral axis. Let's have first moment of area. Let's calculate first moment of area. First moment of area. So I would say first moment of area about that line AB. Let's call it as AB line, AB. So I would say that y bar into total area of 100 into 10 plus 40 into 10 equals to that centroidal area, that centroid and this centroid. So I would say 40, that I would say 100 into 10 acting at 5 from AB, and similarly second one is that 40 into 10 acting at 10 plus 5, 10 plus 5. So this one is your 10 plus 5, 15. This one is 15 and this one is your 5. So 15 and 5. So we got 15 and 5. That means 10 plus 5. Can write 15. So you got this one from the equation that A is that we can say y bar into A equals to summation of yi ai. And we got the value of that location of neutral axis. Actually, it is the location of centroidal axis, centroid. But we know that centroidal location is same as that of neutral axis location. Yeah. So we got the value of 7.857 mm. So the neutral axis is somewhere here. So this is your neutral axis. Now this is your neutral axis, and I would say now I have to calculate the effect of now. What I have to calculate the moment of inertia now. Moment of inertia. See, now we have different areas, and we say let's say the centroid of this part would be here, centroid of this part would be here, and centroid of this part is here somewhere here, and I would calculate those values. So this value we got as equals to 7.857. So I would say I neutral axis equals to, for the first part I would say b d cube by 12, b d cube by 12, 7.857 b d cube by 12, and by the parallel axis theorem, this is acting at the centroid, and I have to see the effect on the neutral axis. So I have this area of 100 into 7.857, and its distance from the neutral axis, that equals to 7.857 by 2. That if I had to do the square of that, AD square. So we got this one. Now we have to say from the top side. So we have small depth of 10 minus 7.857. That equals to 10 minus 7.857. That equals to, let's calculate that. 10 minus 7.857. That is 2.1430. 2.1430. That BD cube by 12. BD cube by 12. BD cube by 12. Plus effect of its, let's say the centroid is here, and there is some distance d2 dash. So this distance. So I write the area, total area 2.1430 into 100, and the d square equals to 2.1430 by 2 whole square. Then after that we have that brass area 40 into 10. Brass area 40 into 10. So I would write 40 into 10 cube by 12. And then after that we have the effect of that from the neutral axis to that center. I would say this distance d3 dash, that equals to, this is 5, and this is your value of that we calculated. That's 5 plus 2.1430. So I would write plus area of 40 into 10, and the center, that d square equals to 5 plus 2.1430 whole square. And you got the value of I neutral axis, that would be equals to, finally you would calculate that, and that comes out to be equals to 4. Some value of 4.0238 10 to the power 4 mm power 4. So let's say you got this value of I neutral axis of the transformed section. You got this one. Now third step is that once you got the neutral axis INA, now you can say what's the value of y max. Let's calculate. You have to calculate the stresses at the top and the bottom. You have to calculate the stresses. You have to calculate the stresses here and the stresses here. Let's calculate the stresses at the top and bottom. So I would say the stresses at the top and bottom. Sigma at the top, that equals to m max y top by I neutral axis, and sigma at the bottom equals to m max y bottom by I neutral axis. So sigma top would be, the value of m max was equals to 250 p by 250 and 250 p Newton mm. That is 250 p Newton mm. And you have y top. The value of y top equals to, this is the value of y top. Total was 20. You subtracted by 7.857. So you write 20 minus 7.857 divided by neutral axis INA, that was equals to 4.0238 10 to the power 4 mm power 4, and this was your y top was also mm, so you got this value. Now similarly you can solve for y bottom also. So y bottom is also having same value of m max 250 p Newton mm. Then after that y bottom equals to the location of neutral axis from AB. So that is 7.857. 7.857. 7.857 mm. Then after that you have neutral axis that INA, that's 4.0238 10 to the power 4 mm power 4. So we are also got this one. Now the thing is that these are the stresses in the transformer section. These are the stresses in the transformer section. These are the stresses we have in this transformer section. Now second final stage is that once you got the stresses in the transformer section, you have to convert them into stresses in the actual section. So you have to multiply the factor with that. You have to multiply that with the factor, modification factor. Yeah, you have to apply the modification factor. Let's say you have to apply the modification factor between the two. So let's talk about which side you have transformed. You have transformed steel into brass. That means if the brass takes stress of, say, we have on the brass side, there won't be any transformation because brass has been changed from brass, so there is no effect of that E. So E brass by E brass, that means there is effect of only one. That means no effect of because brass has been changed to brass itself. So for the top side, you don't have to change the stresses. No, you don't have to change the stresses for the top side. So you got this value of stresses at the top. That should be equals to, if you equate it with the stresses that you are allowing for the brass, you are allowing stresses of 75 megapascal for the brass. 75 megapascal for the brass. So if you equate that, you should say the stresses developed at the top, that should be less than or equal to allowable stresses in the brass. Stresses allowable in the brass, that equals to 75. That equals to 75 megapascal. That should be less than or equal to 75 megapascal. So for the first case, you don't have to apply any factor for the stresses. But if you talk about the bottom side, so actually this value, the value you got here, it's the stresses in the bottom in the member. That's the brass itself. So we have only brass. We have only brass for the transformer section. In transformer section. In the transformer section, this is the stresses in the brass in transformer section. You have to convert them stresses at bottom in the steel, because actually you have steel. So this is actual stresses at bottom in steel in the actual section, I can say. That should be equals to. So your steel can take more stresses. If you talk about the strain compatibility, I would say there would be some neutral axis location. So I would say the strain profile is somewhere in this way. So we know that the strain 1 equals to strain 2. That means strain at brass equals to strain at steel. I would say strains should be same, but because E is different, I would say if you now convert that this value of stress, that should be less than equals to steel allowable stresses in steel, because actually the steel is there. But you have to apply a factor also here, that this was the stresses developed in the brass, but the brass is not there. But the brass is not there. That means your factor of modification factor of M, that should be multiplied, because steel can take more stresses. For the same strain, steel takes more stresses. The reason for this one you can write, for the multiplication of this M means that steel takes more stresses. Steel takes more stresses. Steel takes more stresses than your brass, because ES greater than E bronze. This is actual thing. When you have calculated for E brass only, so you have stresses. You got the stress value, some value of stress equals to this equation. You got some stress value, but you have to multiply it with modification factor of M, such that it would give me stresses at the steel, stresses in the steel, in the transformer section. So this you have to equate with the that should be less than or equal to steel allowable stresses in the steel. That is equals to 112.5. 112.5. That equals 112.5 megapascal. So once you solve these equations, you can get the value of p, different values of p. From the first case, you get value of p equals to, you got a value of p equals to 994.1 Newton, and from the second case you got value of p equals to 921.83 Newton. So we can say what is the maximum value you can apply. So you can say the maximum load you can apply is the minimum of 2, that is equals to 921.83 Newton. So this is the maximum load you can apply on this composite section. So the conclusion is that, I could say that firstly you can say you are provided with the brass and you are provided with the steel, same width was same b. Now you have to say you have to convert them because the stress variation is somewhat in this fashion. So this is the stress profile. Had it been in this way, I would have wrote that sigma max, sigma bottom, and sigma top equals to my by I. So similarly, I could have got the values. But here it is difficult to use that equation. So I would convert it by using transformer section approach. So that says that convert it into equivalent. Let's convert it into equivalent bronze. That means steel changes to, width of steel changes to m times width of bronze. So that means if you make a section, we got some section of I section or T section, I would say this value equals to m times b. This was your b, this was 10, this was 10. Then you calculate the neutral axis. Neutral axis was somewhere here. Then you calculate the moment of inertia about the centroidal axis, I neutral axis. You got a neutral axis. Then we say what is the value of y max at the top, y top, and y bottom. So you wrote the equation stresses at the top in the transformer section, where that was m y top by I, and similarly sigma bottom equals to m y bottom by I. So you got the stresses. Now after that, these were the stresses in the transformer section. Now you have to convert them into actual sections. Stresses top actual. Since this is only bronze, and on the top initially you had also bronze, so you don't have to multiply any factor. So you have to say the stresses you got it here, that should be less than or equal to sigma allowable in the brass. And the stresses on the bottom you got, this is for the brass only. This is for the brass only. This is for the brass, and you have to convert it into steel stresses in the steel. So you have to apply sigma b into some multiplication factor m. That should be less than or equal to sigma allowable in the steel. Then accordingly you got two values of p, p1, p2, and minimum of them is the p max that you can apply. So we take one more problem on this concept. We take one more problem. that you had the section. One is your aluminum, and next one is your copper. Aluminum and copper. Then you have 10 mm. This is also 10 mm. Then the width is 40 mm. So this is the cross section, and you have applied a bending moment of that sagging bending moment of, or we can say pure bending moment of 0.2 kilonewton per meter, 0.2 kilonewton meter. So you applied this moment, sagging bending moments to, that means curvature is somewhat in this way. That means top is having compression and bottom tension. So, but this was for the case if this material was homogeneous. But here we have two different materials, unsymmetric section. And you need to calculate the radius of curvature, because the material is rigidly connected. This is bonded strips. It is bonded strips. Aluminum strip and copper, they are bonded. That means they are rigidly connected. So we have only one neutral axis, and we have only one radius of curvature. So you need to solve for that radius of curvature. What is the value of radius of curvature? And you need to calculate the stresses, the maximum tensile stresses and maximum compressive stresses. Compressive stresses and tensile stresses maximum. So the profile, I would say, let's say the neutral axis is somewhere here. Let's assume the neutral axis is somewhere here. Then you can't directly say neutral axis is at the mid, because it's not a uniform, it's not that homogeneous section. So let's say this neutral axis is somewhere here, so you have some profile, of stresses. Then it would change, it depends on the values, some sort of change would be there, so we will see later. So we got one neutral axis and neutral, so you need to calculate the radius of curvature, and you need to say what's the maximum tensile and compressive stresses. And value of E is also provided. Value of E equals to E aluminum equals to 0.6 10 to the power 5. E copper equals to 10 to the power 5 megapascal. So, and bending moment was equals to 0.2 kilonewton meter. So, if you use the transformed approach, transformed section approach, step number 1, that is transformed section approach. Let's convert that. Let's convert copper changes to aluminum. Let's convert copper changes to aluminum. Then we say modification factor. We can say the one you are converting, you have to keep it in, at the top. E copper by E aluminum. So we can write 10 to the power 5 by 0.6 10 to the power 5. So we got a value of 1.67. So a factor of 1.67 you have to multiply to the width of that copper, so to convert it into terms of equivalent aluminum. So we can say this is our resultant diagram looks like. Let's say this was your initially that 40 mm, and this one would be equals to 40, and this one is your 40 into 1.67, that is equals to 66.67, and this was your 10 mm, this was your 10 mm. So the next step is that calculation of neutral axis. So let's say that neutral axis is somewhere here. I have y neutral axis. Let's say this is y dash. So that equals to that first moment of area about that line, AB line. That's equals to that is equals to 66.67 into 10 acting at 5 plus 40 into 10 acting at 15 divided by total area of 66.67 into 10 plus 400. So you got a value of y bar equals to 8.75 mm. So 8.75 mm is somewhere here. So that means this part is 1.25. So this is 8.75. Now the centroid of this area, centroid is somewhere here, and this centroid is here, and this centroid is here. Now third step is that calculation of neutral, that INA, that second moment of area about the neutral axis. 8.75. Let's solve that. So we can write that BD cube by 12 plus AD square A in D square equals to this 1 by 2 of that. So this is your D square. Then after that plus, then after that you have small depth of 1.25 BD cube by 12. Then plus its centroid is at some distance d2, so I can write 1.25 into 10 into d square, 1.25 by 2 whole square. And after that you have third area, 40 into 10, so I can write 40. Then I can write 40 cube by 2, 40 into 10 cube by 12, 40 into 10 cube by 12 plus its effect of on this that third d3 square. I can write that equals to, this was your 5 plus 1.25. So I can write total area of 40 into 10 acting at 5 plus 1.25 whole square. So finally you can calculate the INA. That would be equals to, overall value of INA would be equals to 33889.635 mm power 4. So you got the INA, total INA. So you got this value. Now, so you got this value. This was the neutral axis, that INA of the transformer section about the neutral axis. So you got 3 steps. Firstly, you converted copper to aluminum, and you applied modification factor of that width. BC changes to M times B aluminum. So you got this one. Now you got this equivalent section. Now you applied Now you applied bending moment. Now you said that what's the location of neutral axis. You got the neutral axis also. Then after that you calculated the value of INA that you also got. Now after that you need to say what's the radius of curvature. The problem says that get the value of radius of curvature. Do you know equation of that flexural formula? M by I, E by R, sigma by Y. So initially we don't know the value of stresses, but we know value of a moment that was provided to you. Bending moment was equals to pure bending moment of 0.2 kilonewton meter. I neutral axis also I know. Radius I need to find, and I have converted it into equivalent E of aluminum. So can I use that equation? Can I use this equation? I think so. We can use this equation. So if we write that moment of that the moment you applied that was equals to 0.2 kilonewton meter divided by I neutral axis weak solid that was equals to 33889.635 mm power 4, and you had equals to E value of E aluminum that was equals to 0.6 10 to the power 5 Newton per mm square megapascal. And after that you have value of R. So that value of R is same because you have rigidly connected members, so you have same radius of curvature for the two those strips. They bend together. So we got the value of radius of curvature equals to 10.1669 meter. So we have sagging bending moment. So top is having compression, bottom tension. So this is equivalent. This is for equivalent section. So now if you want to say what's the next part of the problem was get the value of stresses. So you need to get the value of stresses. Sigma max in the tension and sigma max in the compression. Firstly, you need to say what is the maximum stresses in tension and compression for the transformer section. So this was your transformer section. Let's say this is neutral axis. So I can say maximum stresses would be this is the maximum stresses in the compression because you have sagging bending moment. That is sagging bending moment, positive moment. So top is having compression and bottom having tensile stresses. So sigma T max. So I can calculate. Both are for brass. This one aluminum, because all material is of aluminum. So I can calculate stresses in aluminum at the top and bottom. So if I write that, next step, stage 4, step 4, that's stresses at top in the aluminum transformer section, that equals to M. The value of M was equals to 0.2 kilonewton meter. M y top equals to the value of y top equals to this one. From the neutral axis you have to go 10 plus 1.25, 10 plus 1.25, 10 plus 1.25 mm divided by I neutral axis. I neutral axis is equals to 33889.635 mm power 4. So finally you got the stresses at the top in the aluminum in the transformer section equals to 66.392 megapascal. And you can say stresses at the bottom in aluminum in the transformer section equals to value of bending moment is same 0.2 10 to the power 6 Newton mm, and y bottom equals to the value of location of neutral axis itself, that's 8.75 mm divided by same value of 33889.635 mm power 4. So finally you got this value as value of stress equals to 51.638 megapascal. Can you say this is tensile stress, that compressive stress, and this is tensile stress? Based on the location of neutral axis, can you say that the top stresses would be compressive and bottom stresses is tensile? But it is both are for the transformer section, that's in terms of aluminum. So if you want to say what's the actual stresses at the top and bottom, so actually your section looks like a rectangle. So you had this brass and you had this aluminum and copper. So you got the stresses at the aluminum side. So your equivalent, so actually the equivalent was in this way. So this was your aluminum and this was your aluminum. Both were aluminum. So you got the stresses at the top, and we have same material, same dimensions of that for 40 mm. So we have same dimensions of 40 and 40, and we say that the E is also same at the aluminum side. So we can write that stresses in the transformer section at the top in the aluminum, that should be also equals to actual stresses at the top in the aluminum. So this value is same. There is no change for this one. And for the brass, for the bottom side, you have to convert aluminum to copper. So you have to convert aluminum to copper. So if the stresses in aluminum is sigma 1, stresses in copper would be m times sigma copper, because copper is having more E, that means it would take more stresses. For the same value of strain, your copper would take more stresses. So I would write, so sigma actual in the copper, that's at bottom, that should be equals to m times 51.638. That should be equals to, that value comes out to be equals to 86.064 megapascal, and that should be tensile. First one was your compressive and bottom one tensile. So if you want to plot that stresses, you can say this was your 51.66.392 compressor, and this was your tensile stress of 86.064. Then the variation, it depends on the variation, what was the variation in location of neutral axis, so accordingly. So you could also solve, let's say, if you wanted to convert that, that copper and aluminum, if you want to convert aluminum to copper, that means you have to multiply the modification factor of E aluminum by E copper. That was equals to that 0.6. So that means if the width was 40 initially, so you have to convert that 40, and the width for the aluminum should be equals to, that should be equals to 0.6 into 40, that is 24. So then you can calculate the neutral axis location, somewhere neutral axis location, and accordingly the procedure is same then. So when you got the stresses at the top and bottom, that was in the transformer section for the copper. Then you have to multiply the modification factor of 0.6 at the top, so to get the stresses in the actual aluminum. So let's take one more problem. Let's say now the members were not rigidly connected. So next stage is that we call it as sections. That section simply placed one over other. Simply placed composite section such that the two strips simply placed one over other. That means if they are not bonded, that means they are not bonded, or they are not rigidly connected. That means they have different, that means they have two different radius of curvature, they have two different neutral axes, that is they bend independently. So they bend separately, I can say. So but for the calculation of that, so let's say this was that they have simply placed one over other. Let's say this was material 1, this was material 2. You applied moment of M. So they placed one over other. Let's say depth 1 and depth 2. So if you say that there are two neutral axes, so let's say the neutral axis for the first one is this one, and for the second one we have neutral axis this one. So the stress or strain variation would be in this way. So this is, you can say strain or stress, whatever, because stress is proportional to strain. So this is the variation of that stress or strain. So we have two different neutral axes, Na1, Na2. So we can say to make the calculations easier, we say that they have same radius of curvature. R. We assume that R1 equals to R2, that equals to R. This is the assumption. In this one. We say that they have same radius of curvature. We have the same radius of curvature. Then we say if the total moment you applied you apply total moment of m equals to, you applied a total moment of m. Now, first material and second material, they will resist some moment m1, and second one will resist m2. That is total m. And we said that radius of curvature is same. R1 equals to R2 equals to some value of R. Then from the Bendix's flexural formula, we write m by I equals to E by R. So we can say that value of R equals to, that 1 by R equals to, that value of 1 by R equals to m by EI. So I can write m by EI. So I would write m1 by E1 I1 equals to m2 by E2 I2. So if I convert one into another, I would write m1 equals to m2 times E1 I1 by E2 I2. So if I say that m1 plus m2 equals to total m resisted, the total moment applied on the section should be equals to m1 plus m2. So if I convert this m1 in terms of m2, I would say m2 times E1 I1 by E2 I2 plus 1 equals to m. That means to m2 equals to m E2 I2 by summation of EI II. I can write moment of I equals to m times EI II by summation of EI II. So this is your moment resisted by particular strip. So this is the total moment that is resisted by particular strip, and you know the equation for the stresses. You know that how much stresses you can allow for material 1. That allowable stresses should be greater than or equal to the stresses developed because of the bending moment. Then we can write m1 or y1 by I1. So similarly, sigma allow 2, that should be equals to m2 y2 I2. Then accordingly you can get the values of those unknowns, whichever the question asks. So we have the values of mi. You can substitute here. You also know the value of stress, how much stress we can allow in the material. This is also already known to us, that stress is how much we can allow. Then accordingly you can design the sections I2. You can design the sections, or you can calculate the moments also. But one thing is that if you say value of E is if the value of E is same, E1 equals to E2 equals to some value of E equals to some value of E, that means we say that the stresses in 1 by stresses in 2 equals to d1 by d2. From this equation, if you combine these two equations, one is this and next one is this one. If you say that E1 equals to E2, you would get this relation that stresses in 1 by stresses in 2 equals to d1 by d2. We already understood the concept in the previous class that if the material is not equally strong in compression and tension, then we said that how much depth at what location the neutral axis should be. We said that the depth d1 and d2 should be such that how much allowable stress you can allow in compression and how much allowable stress you can have in tension. Then you say that sigma allowable in tension by sigma allowable in compression equals to d1 by d2 by d1, or d2 by d1. Accordingly, you got the value of neutral axis. Similarly here, we said that if the material is having same value of E, as in this case we have same value of E is same, we said that sigma 1 by sigma 2 equals to d1 by d2. Let's take that problem. Let's take the problem. It's saying we have a problem that is called as a section 100 mm, and you have a steel of 12 mm width strip. So this is your steel of strip 12 mm, and you have wood of 150 mm. This is wood, and you have steel strip. On the bottom side, you are applying a moment in z direction. This is z axis. So moment in z direction. The value of bending moment is positive. So positive bending moment of 16 or 6 kilonewton meter. and I would say the value of E is also given. This value is equals to 210 gigapascal for steel, and value of for the wood is equals to 10.5 gigapascal. Then you need to say what should be the maximum tensile stresses in the wood and the steel. So you need to say the stresses, maximum stresses in the steel, in the wood and steel, but for both, for the both sides, that maximum compressive stress and maximum tensile stresses. So you need to say what is the stresses at the wood on the top and on the bottom, and similarly what is the stresses on the steel at the top side and on the bottom side. So you need to say what's the stress on the top and bottom of the individual strips. So we have to see whether the question asks us that says that material is that rigidly connected. Yeah, material is rigidly connected. Material is rigidly connected. So that means they have the same radius of curvature, same neutral axis. So let's convert by transformed section approach. Let's convert steel into wood. Let's convert steel changes to wood. If the steel changes to wood, that means you can have modification factor of 210 by 10.5, that equals to 20, a modification factor of 20. So if you want to convert the width of the section, so I can say that this was your 150 mm, and the width was 100 mm. This was 100 mm for the wood. Now you are converting the steel strip in terms of wood. So your width becomes equals to 20 times that 100, that is 2000. So that is 20 into 100, that is 2000 mm. 2000 mm strip. So all is wood now. Now all is wood. So I need to calculate the neutral axis location. The depth of that strip was, thickness of the strip was 2 mm. This was 2 mm. So I can calculate the, now second step is that calculation of neutral axis calculation. I would say y bar equals to 2000 into 2 acting at 1 plus, similarly you have 150 into the width was 100 acting at 50 plus 1, 50 plus 2, that is 52, divided by total area of 2000 into 2 plus 150 into 100. So you got a value of y dash. You got a value of y dash equals to 37.2. 37.2. Is it? Yeah. Actually, this was this 52. You have this centroid. So this was 75 plus that value of 2. So 79, I can say this is 79. 75 plus 2, 77. So the centroid of that area is from this reference line, that is 2 plus 75. 2 plus 75. That total 150 here. The problem is that this was provided that this was 12 mm, thickness was 12 mm. So you have to keep the 12 mm here, and you have to take that. Then it becomes equals to 75 plus 12. 75 plus 12. That finally 75 plus 12, that is 87. Similarly, you have this 12 by 2, that is 6. 12 by 2, that's 6. 75 plus 12. 75 plus 12. Let's keep it. So we got these values now. We got these values. 2000 into 12. So you can see that. Is there any correction now? Is everything okay? Everything okay. 12. So everything is perfect. So we got this 2000 into 12. So we got this 2000 into 12 into 6 acting at 6, and this one is acting at 75 plus 12. 75 plus 12. So everything is perfect now. So you got the value of centroid at 37.5 mm. So let's say that the centroid is at 37.5. 37.5 is somewhere here. So this is 37.5. So centroid of first one, centroid of second one, centroid of third one. So we need to calculate those different values of those centroids. Accordingly, we can calculate now third step, that's called as INA. We need to solve that INA. So we need to say third step is that calculation of second moment of area about neutral axis. Let's write for the first that area. I would write BDQ by 12, BDQ by 12 plus AD square. The centroid is at 37.5 by 2, 37.5 divided by 2 whole square. Similarly, for the small area we have this one. The distance of this one would be equals to 37.5 minus 12. That is 25.5. Yeah. So I would write 25.5 whole cube by 12 into your width of 100. So BDQ by 12, and then after that AD square. What's the value of D? What's the value of D? For this area, what is the value of D up to the neutral axis? So this is the value of D. So I would write 25.5 whole square by 2. 25.5 by 2 whole square. Then after that, you had third area. From the top side, you had the third area. Its dimensions are 150 minus 25.2. 150 minus 25.2. That's 124.8. So you can write 124.8 whole cube by 12 into value of B 100. So BDQ by 12 plus area 124.8 into 100. This is your area, and the centroidal distance from the neutral axis for this area neutral axis is at a distance of that 124.8 divided by 2. 124.8 divided by 2 whole square. So we got the different effectors of those contributions of that inertia, moment of inertia. We got this value of INA equals to 89.5790. So you can say 89.5790 into 10 to the power 6 mm power 4. So this step is over. Next step is that calculation of those stresses. Let's say this is the neutral axis. Then we can say stresses would be in this fashion for the transformer section. These are the stresses in the transformer section. So we need to say what is the stress here, and what is the stress here, and what is the stress here. We need to say what are the different stress values at the junction, at the top. Let's calculate the stress at the top. Stress at the top equals to, I would write as the moment we have provided to you, that was equals to 6 kilonewton meter. 6 kilonewton meter into y top. What's the value of y top from the neutral axis? Value of y top was from the neutral axis. This is neutral axis. Value of y top was equals to 124.8. 124.8. So I would write y top equals to 124.8 mm divided by I neutral axis. I neutral axis we know 89.5 790 10 to the power 6 mm power 4. So you got the stress value of 8.42, and we can say this is compressive stress on the top, negative compressive stress. Now you want to say what is the stress at the junction, at the steel and wood junction. At this junction, we want to say what is the value of stresses in the transformer section. So the stresses here. So what is the value of y here? What is this value of y? So value of y at the junction, I can say yj equals to 37.5 minus 12. That is 25.2. So I would write yj equals to 37.5 minus 12. That is 25.2. 25.5. 25.5. 25.2. 37.2. 37.5 minus 12. Let's say that is 37.5 minus 12. Okay. And value of moment is 6 kilonewton meter. And this was mm. And you have to multiply by, divide by 89.579 10 to the power 6 mm power 4. So you got the stress value of plus 1.696. Is it plus or minus? Can you say? What do you think? What should be the value of stress here? Positive or negative? So the neutral axis is above this point. So the point is below the neutral axis. I would say this is tensile stress. So we can write negative stress. Yeah, we can write tensile stress. We can write tensile stress here. This was your tensile stress below the neutral axis. And after that, you have to say what's the stress at the bottom. So stress is at the bottom. Stress is at the junction. Stress is at the bottom. Stress at the bottom would be equals to 6 kilonewton, 10 to the power 5, 10 to the power 6 Newton mm, and value of y bottom that was equals to location of neutral axis, that y na, that was 37.5 something, 37.5. So let's say that value is equals to 37.5 mm, and divided by I na, that was 89.579, 10 to the power 6 mm power 4. So similarly, you got the stresses at the bottom equals to tensile stress of let's say you got some stress value. Let me calculate that. That equals to 2.51 megapascal. Now, these were the stresses in the transformer section. These are the stresses in the transformer section. So we got the stresses in the transformer section. So I got the stresses in the transformer section, that the section I transformed that in terms of this one. I would say I got the stresses. So this was your transformer section, that the width here was equals to 100. This was 2000, and the strip was equals to 12 mm, and the depth for this wood was equals to 150. So I got the stresses. I got the different stresses. If I say the neutral axis was somewhere here, so I got the stresses. I got the stress values. So I got some stress values. Let's say the values we have on the top, we had 8.42. We had 8.42 compressive. Then on the neutral axis we had 0, and on the junction we had tensile stress of 1.696. Then after that, at the bottom side we had stress off. We had some stress value of that we calculated earlier. We had some stress value of 2.51. So we got this value of 2.51. So this was the stress variation. If it was only wood, we'd have a linear variation of stresses. But the section is not the same. We have the section that is actually in this form. We have this section in this form. So we have this strip of steel, and then after the wood, we have wood, and after that we have steel. So we need to say what is the value of stresses here, what is the value of stresses here, what is the value of stresses here. So let's say this is the reference. I would say stresses. So we need to transform stresses to actual stresses. So for the wood, so initially it was wood, and actually it was wood. So we need to keep the wood's stresses as it's. So initially the stress is 8.42. It would remain as it is for the wood. So stress would remain same, 8.42 stress compressive. Then after that, the stresses in the, I would say stresses in the, let's say stresses in the, I got the value of stresses at the wood junction just before, I would say just before the junction. The stresses was equals to 1.696. So the stresses were equals to 1.696. Let's say this is 1.696 initially. But as long as you reach it to the side of that steel, as long as you reach it to the side of steel side, so you have to multiply a factor of m into 1.696. So the stresses at the junction in the steel would be equals to 20 into 1.696. That would be equals to 34 megapascal. So a rise of that stress variation would be, so a rise of that such that the overall stress becomes equals to 34 megapascal. Overall stress value becomes equals to 34 megapascal. This is the overall stress value, 34 megapascal. And after that, we had to say what's the stress value at the junction, at the bottom side. So initially the stress was 2.51. Then you have to multiply a factor of m, such that you got a stress value of stress in steel, that is 2.51 into 20. That's equals to some value of stress equals to 50.2 megapascal. 50.2 megapascal. Let's say 50 is somewhere here. So there is a variation in linear variation. So we got this value of stress. Then after that, when you reach it 1.696, so you go to the neutral axis location. Then you have to make it to 0. Then after that, similarly in the side there is only one material, so there is a linear variation. I would say this is a linear variation. So the stress profile looks like in this way. If you talk about the strain variation would be a straight linear variation, that here the strain is 0, then after that there is some strain. So strain here, strain 1 equals to strain in steel, strain in wood. Here the strain is ES max, and here is the strain EW max. But strain is same here, but the stresses are different because of E is different. So we got the stresses in wood here 1.696, and the stresses in the steel equals to 34 megapascal. So a difference of 20 times that, 20 times the stress in wood. So this was a very beautiful problem. Let's take one more. Let's take one more problem. Let's take one more problem. The problem says that, let's say the problem, what says the problem? Problem is saying that I am a wire of length L and thickness T. I am a wire of length L and thickness T, and such that I am a wire, or I can say I am a rod, such that I am initially in this fashion. I was initially in this fashion. Then you applied some moment M, let's say pure bending moment, sagging bending moment. So the curvature followed a path of sagging curvature. Let's say it was the curvature followed. So on the top we had compression and bottom tension. So we got this. Now it's saying that the deflection at the mid. It's saying that the deflection, let's say this is the neutral axis. It's saying the deflection at the mid, let's call it as a D. It's saying the deflection at the mid is very, very less as compared to the length L. Now it's saying that get the value of strain. Let's say the thickness is D. Get the value of strain, longitudinal strain, in terms of function of, as a function of thickness, that depth, length. Get this value of strain in terms of these variables, these parameters, I would say. We know that strain. What is the equation for strain? We know that strain equals to y by r. Do we know that strain equals to y by r? That longitudinal strain equals to y by r. So let's say, what is the value of y max? We can say, what is the maximum strain we can have? So if you go from this neutral axis to a y value of, so y max, we can say y max equals to thickness by 2. Let's keep it on this side. So if you observe the profile, we say that along the neutral axis, if you make a circle, let's make a circle. So we say this is your D. That means this part, left part, we have that's 2 times r minus D. Can you say that total diameter is D? Total diameter is 2r, and you subtracted by that depth value of D, 2r minus D. And by the property of triangle circle, we have this property of the circle. Let's say the length was L by 2, and this was L by 2. This is depth, and this is 2r minus D. We said that let's call it as A, B, C, D. We say AB equals to CD. we say this one, property of circle. AB equals to CD. Similarly, we write L square by 4 equals to 2R minus D into D. So you solve this, you can get L square by 4 equals to 2RD minus D square. Now, if you convert this, if you say 1 by 4 equals to 2RD by L square minus D square by L square. So we got this relation, and initially we got the strain value. That strain along the longitudinal direction equals to Y by R. Strain equals to Y by R. And the value of Y, if you substitute the value of Y equals to Y max, if you substitute the value of Y max equals to T by 2, so we can get the value of T by 2 R. Strain equals to T by 2 R. T by 2 R. Now we can have the value of R here. We can have the value of R here from this equation. Now, one thing was given to you in the problem that the deflection at the mid, that's very less as compared to the length L. So if we say the depth is very less as compared to the length L, so this value is, I can say, negligible. This value is negligible. So we can write that. We can write then 1 by 4 equals to 2RD by L square. So we can ignore this term now. So we are left with that R equals to 8 L square by D. R equals to 8. Yeah, L square by 8D. So we got the value of L square by 8D, that equals to R. L square by 8D equals to R. L square by 8D. So if I substitute the value here, I would write T by 2 L square by 8D. So we got the strain as a function of 4 TD by L square. 4 TD by L square. Let's take two problems. Let's take the problem that involves stress transformation also. Stress transformation. So we have a wire. We have some wire of thickness 2 mm, or we can say diameter is 2 mm of the wire. That's wound round a shaft, a circular shaft, 1 meter diameter. So that diameter of the shaft is 1 meter, and you wound that wire around that shaft. So you need to say what's the maximum normal stress sigma 1, and what is the maximum shear stress tau max in the wire. One thing is that, and also get the location of theta p and theta shear. And the wire, we can say modulus of elasticity of wire, the Young's modulus of elasticity of wire, E wire equals to 10 to the power 5 megapascal. One thing is that assume no pull tensile stress. Assume no pull, or we can say no tensile stress applied. No pull tensile stresses on the wire. There's those stresses applied on this wire, but you have to say you take a shaft. Let's take a shaft. Let's say this is the shaft, and around that you had some wire. Let's say this is some wire. Let's take this as a wire. So I would say this is the wire. This is the wire of thickness or diameter phi equals to, the value of that wire equals to phi 2 mm, and the diameter of that circle, that shaft equals to, this diameter equals to, this equals to 1 meter. So if I say that your wire is wound around a circle, if you say the wire bends in the form of arc of a circle, let's say the wire bends in the form of arc of a circle. Let's take this neutral axis. Then I would say if you cut that particular section of that wire and you analyze that particular section of the wire, and you would say it's around that circle of radius equals to, this is some radius equals to r. So that value of r equals to, I would say, total value of 1 meter by 2 plus that thickness by 2. So radius of, I would say, 1000 by 2 plus 2 by 2. So 501 mm, I would say. A radius of 501 mm is there. So radius of curvature, we can say that is 501 mm. So we need to say maximum stresses. If I know the flexural formula, sigma by y, m by I, E by R. So we don't know the value of moments here. So I can get the how much stresses we can allow in the, I can get the stresses allowable in the wire based on the fact that if I know EI by R, EY by R. If I know the E value of wire, we know that the value of E for the wire is equals to 10 to the power 5 megapascal. If I write that 10 to the power 5 megapascal, and value of Y, so you have some wire, so there is some diameter of that wire, that is 2 mm. So maximum, how much maximum Y can go, Y max? What's the value of Y max I can have? That is 1 mm, T by 2, or diameter by 2. So I write 1 mm divided by radius of curvature. So that's 501 millimeter. So we can say sigma allowable in the wire, sigma equals to, that's almost equals to 200 megapascal. Almost equals to 200 megapascal. Or exactly, if I say that is 1996 megapascal. Let's approximate it to 200 megapascal. Let's say 199.6 megapascal. Then we say that there is no any other pull or tensile stress acting. There is no pull or any load acting outside. So we say that this is the maximum tensile stresses we can allow. We can allow this much amount of stress. So we have this wire. How much stresses we can allow? So the bending stresses would be, maximum bending stress we can allow, sigma max, that should be equals to 199.6 megapascal. So if you have that section, if you take any stress element, I would say you can allow a maximum tensile stress of sigma allowable. Sigma can be allowed that is equals to sigma 1, that equals to 199.6 megapascal. So if I say what's the location of principal plane, the principal plane is the plane itself. I would say this is the principal plane 1, and next one would be this one, principal plane 2. And if you say what's the location of shear plane, I would say go to the theta shear equals to 45, and you can receive a tau max value of some tau max value of, I would say tau max equals to sigma 1 minus sigma 2 by 2, that is 199.6 by 2, that's almost equals to 100 megapascal. So I would say tau max at 45 degree from principal plane 1 anti-clockwise. So this was the end of the problems. So one thing is that final concept of that bending stress, that we call as shaded section. Shaded section. So we say that you have some cross section. Then from the neutral axis, you take some area of the shaded. You take some area that we call a shaded area. You want to say what is how much force the shaded area resists. How much force the shaded area resists. So if the material is homogeneous, I know that from the bending stress formula, I know that the stress variation would be in this way. That this would be sigma max at the rate of y max. And similarly, if I go to some value of sigma here, let's say I take at the centroid, if there is some value of sigma here, let's say this is the sigma here, I would say the value of y is somewhere here, that we can say that's some value of centroid yc. So from the similar triangles, I can say sigma max per y max, that equals to sigma by yc. That's an approximate value that we take the, for the area, for the entire shaded area, we take only at the centroidal value. We take the stress value only at the centroidal value of that particular shaded area. Actually, actually we should take the strip. Let's say this was your shaded area. We should go from the neutral axis to some value of y, then thereby we take some strip dy. We take some strip dy. Then after that we integrate it from that y1 to y2. This was your y2. Then accordingly we can get the overall value of stress that this area can contribute. But we are approximating. This method is that saying that you only solve for the at the location of centroid, from neutral axis. So this equation we can use. We know that particular shaded area is having some area of, let's call it as A shaded. AS represents A shaded. Let's say it's having some area of A shaded, AS, and we know that force equals to sigma into A. Let's call it as A sigma shaded and A shaded, and I would say then I can calculate this sigma shaded equals to sigma max by y max, into yc. So if I substitute the value of sigma s equals to force shaded A shaded equals to sigma max by y max, stress equals to force per unit area. Stress equals to force per unit area. So stress is force by area. Stress equals to force by area. Y max into yc. So I can get the value of how much force that shaded area can resist. That resisted by that shaded area, that's sigma max yc into A shaded by y max. So this part represents that first moment of area. That's first moment of area shaded about neutral axis. Can we say that this is the first moment of area of that area A shaded about neutral axis? So if I have one gate problem, we have this problem in the gate exam that says that you have the neutral axis of this section. Total dimensions are 100, 150. This one is your neutral axis. So it's saying that we have applied a sagging bending moment of m sagging equals to 16 kilonewton meter. Now you have to say what's the force that the shaded area can resist. How much force that shaded area can resist? The shaded area, I can show you that is somewhere here. Dimensions are 25, 50. Let's say this is 25. This is 50. So this area you have to say dimensions are 25 and 50. So from the neutral axis you can say where is the centroid? So we can say yc equals to 25 by 2. And area shaded, how much is the area shaded? That's 25 into 50 mm square. So we got this one. And I can say that force resisted by that shaded area, that is equals to sigma max by y max into your value of yc into AS, that's 25 into 50 mm square. But I don't know the value of sigma max, how much this material is of some particulars material. I don't know the value of sigma max I can allow. But y max I can say that y max equals to 75. So I need to convert that sigma max in terms of y. That another formula, if you have from flexural formula, m by I, sigma by y, E by R. We have provided that sagging bending moment of 16 kilonewton meter. If I substitute that value here, if I use instead of this part, if I use this part, can we do that? So I can write Fs equals to m by I. If I write value of m equals to, value of m was given to you 16 into 10 to the power 6 Newton mm, and the value was yc into as, you know already that and we know value of I about neutral axis. This is I about neutral axis, INA. I know the value of INA, that's BD cube by 12, BD cube by 12, mm power 4. So finally, you substitute those 4 values, we can get the force resisted by that shaded area that equals to 8.89 kilonewton. That is tensile tension, because your area is below the neutral axis, so this is tensile stress, tensile strain, and tensile force. So we can resist a tensile force of 8.89 kilonewton. So one more problem of that particular kind is that you have this section. Now the shaded area is that middle 1/3. So you have B, you have total depth of D. So this is D by 3. So you want to say what's the moment, how much moment that shaded area can resist. How much moment that shaded area can resist. We have that material is homogeneous, that central axis is the neutral axis. So we have this neutral axis. So we can say we have the equation that already we know that sigma max by y max equals to sigma by y. So similarly, that equals to m by I. So that was equals to sigma was equals to some force into area shaded, and this was some value of centroid. Now how can we solve this one? For this one, we have equation of that moment shaded on that similar grounds. We have that moment shaded equals to that value of moment shaded equals to sigma max by y max into value of I neutral axis. That is second moment of area. That is second moment of area about that second moment of area of that shaded area. Second moment of area, I can write second moment of area A shaded of that particular shaded area. You have to get the second moment of area about neutral axis. So I write it as ISNA. Now I can get the values there. Can I get the values now? So is there anything provided that let's say the total moment applied is m. Let's say the total moment applied is m. We want to say how much moment this part can resist. How much of that total moment this part can resist. But stresses we don't know. We don't have given to you any value of stresses. So we have to convert it in terms of m. Let's say the m shaded equals to some value of m that you can apply. Let's say the m max you apply. M max applied equals to m. Let's say the m max applied equals to m. So you can write m by BD cube by 12 into ISNA. What is this ISNA? That's integral y square dA. Second moment of that area about neutral axis. So we can write that. So since the area, the centroid of that area is passing through the neutral axis, so there is no use of parallel axis theorem. So that means d square equals to 0. We can say. So finally, you can write that b d cube by 12. That particular d cube by 12, b d cube by 12. So you can get the 27, m by 27. So the total moment resisted by that middle third part of that area, that's only m by 27. We know that in the bending stresses, that maximum stresses that are developed in the extreme fibers. So the internal members do not get a sufficient amount of stress, so they can resist less stresses. They resist less stresses. That means out of that total external moment m, they resist only m by 27. You can have that from this equation. M by 27. That's very less. If you say how much percentage of that moment they can resist, 27 inverse into 100. That's 3.7%. That's 3.7% of that total. 3.57% of that total m. That means 96.3% is resisted by from the other two, or we can say 48.1. 5% is resisted by other two, top and bottom, m by 3. That d by 3. Do you got this one? So this is the end of that chapter of binding stresses of the beams in the civil engineering structures. Hope the structures remain safe and serviceable. Hope the structures remain safe and serviceable. See you in next lecture. Thank you for watching this series of SOM.